Think about two buildings that look identical from the street but house completely different businesses inside. Or imagine two different keys that share the exact same jagged profile but are made of different metals. In the world of chemistry, we see this strange overlap all the time. Molecules can be twins in ways that aren't immediately obvious, and understanding these relationships is a bit like cracking a secret code. Let's start with the first layer of this code. The prefix iso means same, and electronic refers to the number of electrons. So isoelectronic compounds are simply different atoms, ions, or molecules that possess the exact same number of electrons. To visualize this, let's look at a simple sequence on the periodic table. Picture a neon atom. It sits comfortably with 10 electrons. Now, look to its left at fluorine, which has 9, and to its right at sodium, which has 11. If the fluorine atom gains 1 electron to become a fluoride ion, and the sodium atom loses 1 to become a sodium ion, what happens? They both now have exactly 10 electrons. Despite having different nuclei and different charges, they are now isoelectronic with neon. As you can see, their electronic blueprints have become identical. This is why isoelectronic species often share similar trends in their chemical behavior, though their sizes will vary based on how many protons are pulling those electrons inward. But it gets more interesting when we move from single atoms to entire molecules. Take carbon monoxide, CO, and nitrogen gas, N2. Let's do the math. Carbon has 6 electrons and oxygen has 8, totaling 14. Nitrogen has 7, so 2 nitrogens also give us 14. They are isoelectronic. But notice something else about them. Since they have the same number of electrons, they also tend to distribute those electrons in the same way. Both molecules are held together by a sturdy triple bond. This brings us to our second concept, isostructural compounds. Isostructural species are molecules that have the same physical shape and geometric arrangement of atoms, regardless of which elements are involved. Think of it as using the same 3D mold but pouring in different materials. Let's look at a classic pair, the chlorate ion and xenon trioxide. They look completely different on paper, but if we apply VSEPR theory, the rule book for molecular shapes, we see a pattern. Both have a central atom surrounded by 3 oxygens and 1 lone pair of electrons. Because the electron geometry is the same, both molecules take on a trigonopyramidal shape. They are isostructural. Now, here is the key insight. Just because two things are isoelectronic doesn't mean they are isostructural, and vice versa. But when molecules are both, that's when the magic happens. Take the boron nitride pair and diamond. Boron has 5 electrons and nitrogen has 7, averaging out to 6 per atom. That's exactly what carbon has. When they crystallize, boron nitride can form a structure virtually identical to a diamond lattice. They are isoelectronic and isostructural, resulting in a material so hard it's often used as a substitute for industrial diamonds. So the next time you look at a chemical formula, don't just see letters and numbers. Look closer at the electron counts and the spatial arrangements. In chemistry, identity isn't just about what you're made of. It's about how many parts you have and exactly where you put them.